So, hello everyone, welcome to week 4 discussion session. Hope I'm audible, right? Okay, okay, then let us start. Okay, fine. So, today we'll be looking at various problems related to designing of this this different logics like inverters and NAND gates, NOR gates, and all, and how to do the appropriate sizing and what are the things that we should consider while designing them. Basically, what we want is we want to reduce the delay, we want to minimize it so that we get the optimum, the best performance. So I hope you have gone through the lectures, and I'll be going through the previous year's assignment problems so that it will be helpful for you to come up with the solutions of this year's assignment. So let's begin by looking at the first question. Okay, so first question is, uh, consider a unit inverter driving another unit inverter. Choose the statements about the circuit. Okay, then let me draw the inverters first. Consider. So I have two unit inverters. So this would be the sizings. This is VDD. This is VDD. Okay. So this is basically my input, and this is basically my output. Okay. Okay, so first statement is given that t propagation delay for falling edge is falling edge input to x. Let me call this one as x. This one as x. Okay. Input to x is ln to 3rc. Now let us look what are the capacitances that are involved here. So you can see due to this NMOS, the capacitance would be here 1c, right? It is 1c because it is an unit NMOS, and the capacitance involved here is 2c, right? Similarly, the capacitance involved here would be net capacitance 1c due to this NMOS and 2c due to this PMOS, so here 3c. I have clumped these two capacitors as 3c here. Similarly, the the capacitance here due to the gate of the second stage inverter would be 1c plus 2c. So I'll be writing it as 3c. I'll be clumping them together and I'll be writing here as 3c. And same thing for the second stage output, it would be 1c for the NMOS and 2c for the PMOS. Okay, so here you can see here there are total 1 2 and here 2, so total 4 components of capacitance are present here. So the net capacitance in the node x would be, in node x would be, c of node x would be 2c plus 1c plus 2c plus 1c, which would be equal to 6c, right? Now the first statement is t propagation delay for falling. So for falling from input to x, the my path will be, this one will be my path for discharging, right? This one will be my discharging path. So what would be the, let me simplify and redraw it. So this is the model. So here it would be r, it would be c, the value of let me call it c dash. C dash would be, sorry, not c dash, let me call it cx. It would be 6c, this capacitance, right? And it would be r only because it is an NMOS, and for unit NMOS the resistance is r only. So we know the delay would be log 2. Why log 2? I have done the proof in the first class also, in the previous class also, how we are getting this log 2 value. Here delay would be equals to delay, that is t propagation delay for falling from input to x would be equals to ln2 into r into the cx is basically 6c, so ln2 r into 6c, so it would be 6rc ln2, and here it is given 3rc ln2, so it is false. First one is false. Okay, now the second one is t propagation delay rising, so my pmos stack would be involved. The pull-up stack, the nmos stack is called the pull-down stack, this stack is called the pull-down stack, and the pmos stack is called pull-up stack, right? Because pmos pulls up the voltage to vdd and nmos discharges the output, pulls down the output to this ground, so nmos stack is called pull-down stack, and pmos stack is called pull-up stack. Okay, so the second one is t pull down t propagation delay for rising from input to x is 6rc ln2. So let's see what it is. It would be similar because here it is r of nmos, sorry, here it is r of nmos. When considering t pull down for rising from input to x, the circuit would become something like this. Here it would be r of pmos, and here it would be cx, which is equals to 6c, right? So r of pmos is equals to r of nmos because w of p is twice, so mobility is half, so we'll get the net resistance as same. So if I take rp equals to rn equals to r, okay, I have taken rn, rp and r to be equal because they will be equal, right? So my here this delay would come to be t propagation delay rising from input to x would be ln2 r into cx, that is 6c, so ln2 6rc. So second statement is true, it is true. Okay, now third one, t propagation delay from x to output, from x to this output. Okay, now you can see from here, from this one, the output capacitance, that is C output, is nothing but these two capacitances, so it is 2c plus 1c, that is 3c, and it is as it has been mentioned, it is the falling delay, so my this nmos is involved, this one is involved in discharging this. Okay, so it would be again r of nmos, which is equals to r, and output is 3c. Okay, c output is 3c, so my delay would be log ln2 r into 3c, 3rc ln2, so it is also true, second one is also true. Finally, it has been mentioned that the fourth condition is t propagation delay falling for x to output is ln2 6rc. No, it's not wrong, because here also propagation delay falling, here also propagation delay falling, we have seen it is 3rc and not 6rc, so it is false. Okay, so my correct sequence is false, true, true, false. False, true, true, false. Okay, any question? I hope it's clear. Okay, now the next question is, what is the Elmore delay at the output node? It's a very simple circuit. Let's look into a little bit more complicated circuit. Okay, okay, this is my input, this is my output. Okay, so let me call it R1 C1 R2 C2 R3 C3 R4 C4. Now the simplest way to remember this is, when considering finding the delay, the Elmore delay between two nodes, the first condition is the capacitances should be always between particular node and ground. There should not be any capacitance between node to node. So such kind of circuit is not possible. We cannot analyze such kind of circuits. Okay, because here intermediate capacitance is present, we cannot analyze them using Elmore delay model. So the capacitance should be between any node and then and the ground. So while considering such circuits, the simplest way to remember them is the net delay would be the resistor that is present in the active path, that is the path between the input and the target node, and the capacitances like these resistors will only come into picture, and the resistors like this R4 which is not present in the active path will not come into picture, but all the capacitances would lead to the would contribute to the net delay. So all resistors will not lead to contribute to the net delay, but all capacitors will contribute to the net delay. And we can, how we can remember this is, see this C4 is present here. If I remove this R4, what basically happens, this C4 basically becomes Uttara, can you kindly mute yourself? Hello. Uttara, can you kindly mute yourself? Noise is coming. Hello. Okay, I have muted her, no problem. Fine. Okay, so you can see if the resistors which are not present in the active path, we can think these capacitors to be present in parallel with this node. Okay, so basically my R1 would contribute, and R1 would lead to charging of this C4. So this C1, C4 and all the capacitances that are present in this node can be considered to be in parallel. So there will be simply we'll get to find the sum of them, simply these capacitances. Okay, so the net delay here would be R1 C1, because we have this V input has to charge this C1, then it has to charge this C2 through this R1 and R2. So R1 plus R2 into C2 plus this C3 will also come into picture. So R1 plus R2 plus R3 into C3, that is, it is charging this C3 through this R1, R2 and R3 through this path. And as R4 would not come into the picture, but C4 would come into picture, R1 C4. Okay, so this is your delay, will be this delay for this circuit. So the and this circuit is very simple. So what will be the net delay here? You can see this is your input node, this is your target node, V out, V input and V out. So here it would be simply, a delay would be simply, it would be R1 C1, because you have to charge this C1 through this R1 C1, and you have to charge this C2 through R1 and R2, right? So R1 C1 plus R1 plus R2 into C2. Which one matches this? R1 C1 plus this one, R1 plus R2 into C2. So it's very simple. Generally Elmore delay and all these are very simple things. Okay, and in the SPICE model, like when the circuit does this simulation, they generally doesn't do this Elmore delay. They does other kind of simulations, because these delays, as you can see, this takes some considerable amount of time for calculation. So the error is not that much, but the computation time is reduced when we move to other kind of delay computation algorithms. Okay, but it is a very useful method to compute the delay of a given circuit. Okay, if we have the idea about the resistances and capacitances that is present in my circuit. Okay, okay, let's move forward. What is the Elmore delay at node 1? Same thing, this is the node 1. If we would have been asked about node 5, what would it, which are the resistors, which are the active paths, this would have been my active path. So my R3 and R6 would have not come into picture, only this resistors would have come into picture. If we were asked about this, then this would have also not come into picture, only this would have come into picture, right? Similarly, if R3 was like this, if this was our target node, then this resistance would have come into picture, and so on. Now, as this node has been asked, so simply my R1 would come into picture, right? So it would be, the delay would be R1 C1 plus R1. R2 will not come into picture, we will just consider this one to be as in the same node as this one, R1 C2. Similarly, this one R1 C3 plus R1 C4 plus R1 C5 plus R1 C6. So basically it would be R1 C1 plus C2 plus C3 plus C4 plus C5 plus C6. Simple. This one. Clear? I hope there is no confusion, right? These things are very easy generally. Okay, fine, let's move forward. Okay, fine. Okay, question number 4. So it is given that if R is 10 kilo ohm and C is 0.1 femtofarad, and the electrical effort is given as 4, determine the propagation delay for a circuit with a W scaled unit inverter driving M unit inverters. So what has been given to me? They have given that I have one W scaled inverter, that is, this is W and this is 2W, and what I have M unit inverters, which has been driven by this W scaled unit inverter. So basically it would be such kind of configuration, such kind of architecture, such kind of circuit. Okay, now R is given as 10 kilo ohm, C 0.1 fem2, and H as 4. Okay, so sir has simply given us the formula. T propagation delay is 3RC 1 plus H, but let us see how it is coming. Okay, okay, so basically here the capacitances that would come will be 2WC for this PMOS and WC for this NMOS, scaled NMOS and scaled PMOS. Okay, so my net capacitance here would be 2WC plus WC, that is 3WC. And as these are unit inverters, so here the capacitance due to each unit inverter would be 1C plus 2C, that is 3C. Okay, 1C plus 2C, that is 3C. And as there are H such inverters, the capacitance that would come here is H into 3C, right? Because if there are two inverters, it would be 3C plus 3C 6C. If there are 10 inverters, then 3C plus 3C 10 times, that is 30C. And if there are H inverters, it would be 3C plus 3C H times, that is 3HC, right? So the net capacitance here would be 3HC. Now what is the resistor here? As it has been scaled by W, my resistor would become R by W here for the discharging path, and for this discharging path, and even for this charging part, it would be R by W. Okay, so what will be my propagation delay? It would be R by W into 3WC plus uh, plus R by W into just give me a minute, R by W into, okay, 3C is there something wrong? 3RC RC plus 3RCH. Okay, here R by W will not come, it would be R, okay, it would be R into C into H into 3HC, sorry, 3HC. Okay, it would be cancelled. If I 3RC, if I take common, it would be 1 plus H. This is how he is getting this expression. Okay, so basically 3R is how much? R is 10K. C is how much? 0.1 femto, that is 10 to the power minus 5, 15 femto, and 1 plus H is 4. So it is basically 4 plus 1 is 5. So it is basically 5 into 3, 15. 10K is 10 to the power 4, and minus 10 to the power, this 10 and 0.1 I can cancel, so 10 to the power minus 12 second. So this is 15 picosecond. 15 picosecond is the answer, right? Yes. This one. Yes. This input. Like this point you're talking about? Like, are you talking about this node? Actually, I'm not getting your question. So, what is your question basically? That this capacitance should be at the input you are saying. See, if you remember in the last class, I told that there are multiple capacitances present in a MOSFET, right? If this is my MOSFET, there are how many capacitances that is present in this MOSFET? There are basically five types of capacitances present. Okay, it is my gate, it is my drain, it is my source, it is my body. Remember, there are three oxide related, that is gate related capacitances, and three body related capacitances, and two of them are common, so there are total five capacitances. One is this CGD, one is this CGS. Okay, so one is this CSB, one is this CDB, and another is CGB. Okay, so this capacitance that you are talking about is the gate related capacitances. So this would be 3C, and this would be 3WC, and this is the for it is the drain. This is the drain related capacitances. So this is also be equal to 3WC. So both at the input and the output we will be seeing 3WC capacitance. Okay, sure. Okay, just give me a minute. Okay, M unit inverters. Okay. Okay, I've done the nomenclature wrong, I think. Okay, it would be M. Okay, and as these both were 4, so it was no problem. The answer came correctly, but it should be M. Yes, you are correct. Okay, fine. Okay, thank you for the clarification. Okay, I hope it's clear, right? Okay, moving forward. Uh, Fine. Okay, the next question is, for a 3 input NAND gate designed to have equal rise and fall time of a unit inverter, choose the correct statements. So let us first draw a 3 input NAND gate. Okay, so basically what it would be, 3 PMOSes. VDD. Okay, so this would be my output, this 3 will be my inputs. Okay, so it would be, let me call the 3 inputs A, B and C. A, B and C. Remember, in such kind of circuit, if you can figure out the sizing of this transistor, then you're almost the more than half the work is done. Okay, so you have to just carefully check and what will be the sizes of each transistor. Okay, so as we want the delay to be equal, the worst case delay to be equal, so, and that to be of an inverter, the unit inverter. Sorry, so what it would be, the resistance should be, as there are 3 transistor present, and the net resistance should be R, which was for the case of a given unit inverter. For this circuit, we want these resistances to be equal, right? Like it was R, we want this to be R. So each should be equals to, resistance should be equals to R by 3, as they are connected in series. So what would be their sizes? We know the resistance is inversely proportional to W. So it should be 3, 3 and 3. That is thrice of initial value. Okay, and as these PMOSes are in parallel configuration, what will be the worst case? Only one of them is on. Let me consider, for example, only transistor, this input A corresponding transit PMOS is on, other 2 are off. So still, as it is in parallel condition, the resistance still would be the previous resistance. So the previous sizing would work perfectly. That is 2, 2, 2. If all the 3 are on at a time, then what would be the resistance? 2 by 3. Like the what happens for a parallel, 1 by R equals to 1 by 2 plus 1 by 2 plus 1 by 2, that is 3 by 2, that is 2 by 3 net resistance. Okay, so we are talking about this propagation delay, the worst case delay. And if I was talking about this contamination delay or the best case delay, then I would have considered all the 3 transistors to be on. But for propagation delay, I will be considering the worst case possible condition, that is the highest R, that is only one of the PMOS is on. Okay, fine. So this is my okay. Now let me check what are the capacitances that is coming. This two will be connected, so it will be seeing 2C plus 3C, that is 5C. It will be seeing here. All the inputs will be seeing 5C. Okay, but let us see what the question has been. What are the statements that has been given? So the first statement is, for a rising output, the resistance of an individual PMOS must be R by 3. Individual PMOS, as we have seen, the initial value, that the unit inverter had, that is 2 and 1, is sufficient for the worst case delay to be equals to the case for a minimum the unit inverter case. So I don't need the resistance to be R by 3, simple R would suffice. Okay, so it's a false statement, therefore it's false. Okay, the second statement is for a falling output, the resistance of an individual NMOS must be R by 3. It will be falling through this NMOS stack, the pull down stack, and as I have seen, to ensure minimum delay of the minimum delay, that is the delay of an unit inverter, I need each transistor to have resistance of R by 3. So it's true. Second one is true. Now third statement is width of each NMOS is 2. No, as we have seen, to support this resistance R by 3, or to achieve this, better term is achieve, not support, to achieve this resistance of R by 3, we need a W of 3, thrice of initial value, thrice of that of an unit NMOS of an unit inverter. Okay, so it's not 2, it's 3, therefore this is also false. And the final one is width of each PMOS is 2. Width of each PMOS is 2. It's correct, right? So it's true. So the correct sequence is false, true, false, true, false, true, false, true. Clear? Any confusion? Any confusion? Anyone? You can take a moment and think if you have any confusion. Hope there are no confusions. Okay, thanks for the thumbs up, Divya. Okay, fine. So let me I don't know whether it has been discussed or not. Let me talk about another interesting thing, this propagation delay and contamination delay. See, while considering the propagation delay, we are considering the worst case possible, and while considering the contamination delay, we are considering the best case possible. So in case of this PMOS stack, I told you that when one PMOS is on, it is my worst case, and when all the three PMOSs are on, my net resistance come down to 1/3 of the initial case. So my it is the best case. So it is the contamination delay case. Now what about this NMOS? This stack that I am talking about, when it would, like, this is resulting in the worst case, when it will be resulting in the best possible condition. Let us look into it. See, here a capacitance of how much? 2 plus 2 plus 2 plus 3, that is 9C is connected. Okay, and here a capacitance of 3C, and 3C has been connected, right? Now one more thing, why it is 3C and not 6C? Sir has explained in the class. Anyone? Why it is this capacitance is 3C and not 6C? Because as there are two terminals, one source of the one source of this one and the drain of this one, source of this one and drain of this one. So there should be two capacity terms, right? 3C plus 3C. Why I am only considering one 3C? Anyone? Okay, let me tell. Like sir has already discussed in the lectures, what happens, we have to look into the layout of the circuit if we have to find what is the capacitance between what is the common capacitance between these two. Okay, what happens generally, there is something called as an uncontacted diffusion capacitance. Okay, and in VLSI, by contact, what do you mean? Contact is present means metal layer is present. Okay, so if it had been happened that after this first transistor there was a metal layer, these are the metal layers, if it was present, then I would have got this 3C plus 3C as 6C. But what they do, they design only one N plus or P plus region for both these transistors. Okay, so this one is common between them, and there are no metal layer present between them, that is there are no contacts present between them. That's why as they are sharing their n plus region, we only get one 3C term and not two 3C terms. Okay, as these NAND and NOR gates are of simple architecture, you can, by seeing only, you can say that whether it is uncontacted capacitance or diffusion capacitance or contacted capacitance. Okay, but if we go to large circuits, complex circuits that generally are present in processors and all, or that generally we fabricate for industry oriented applications and all, there it will be very difficult just to look into them and tell what will be the capacitances. On that time we have to do the physical layout of the whole architecture. After that we can say, after doing this physical layer, designing, we can say what are the capacitances present between them. Okay, and now I was going to talk about this worst case, this contamination delay and propagation delay. So propagation delay is the worst case delay, and for propagation delay I am considering when all these three transistors get on at once, this uh, the output needs to get discharged from this one, from this one, and from this one, right? I need to discharge all these three capacitances. This is the case of propagation delay, worst case. Now in case of the contamination delay, what will happen? I will consider that it is the best case delay. I will be considering that, sorry, what I will be considering that these capacitances are already discharged. That is, this signal came much before this signal, and they have already been discharged. Okay, they have already been discharged, and when this signal comes, it has to discharge only this 9C capacitance. Okay, so this Elmore Delay model, like this 3C and 3C would be terminated, this 3C and 3C would be terminated, only this 9C would be remaining. So the delay that we will be getting will be much lesser than the case that we are talking about. So it is the best case condition, and it is called the contamination delay or best case delay. Okay, and see, and you have to understand, so like this logic is generally used, like this concept is generally used when you want one of the inputs to be much faster than the other inputs. Okay, it is called when one of the inputs is needed to be more critically timed or more faster than other inputs. What we will do, we will generally connect them towards closer to the output node. Okay, so because it has so that others capacitances doesn't come into picture and they get kind of discharged initially only, and the critically timed input is generally connected to towards close to the output. So it is something I wanted to tell you. You can keep that in mind during circuit design and all. Okay, these are some small things that is interesting to know about. That's why I'm just telling you about this. Okay, and one more thing, yes, no, that's fine, please go ahead. Okay, fine, let me repeat again for you. Okay, so it has been given that for a rising output, that is my output is rising. Okay, for a rising output, the resistance of an individual PMOS must be R by 3. So there are three PMOSes here. You can see one PMOS, two PMOS, second PMOS, third PMOS. This is the first PMOS, this is the second PMOS, this is the third PMOS, correct? Okay, so it is saying that now to ensure the delay, uh, first of all, it has been mentioned that my rise time and fall time should be equal to that of an unit inverter of this circuit, right? Of this circuit, its rise time and fall time should be equal to the rise time and fall time of this circuit. So in order to achieve that, what I need to ensure, I need to ensure that the delay, the rise time, that is the delay, or from where this delay is coming, from the current, right? From the current and RNC values. Okay, so I need to ensure that delay is basically RNC R multiplied by C into something constant. So I need to ensure that my net RNC value are designed in such a way that the delay that I am getting for this one, the delay that I will be getting for this one and this one would be equal to that of this circuit, this rise time and fall time delays. Okay, so that's why what we will be doing, we will be appropriately sizing these transistors, this PMOS stack and this NMOS stack. Now, in order to achieve the net resistance as R, the net resistance as R, sorry, the net resistance as R, what I need to do, there are 3 NMOSs present here, correct? As let me consider the resistance of each NMOS is R dash. Okay, so the net resistance of 3 NMOSs would be R dash plus R dash plus R dash equal to 3 R dash. And from the question it is mentioned that they should have equal rise time and fall time to that of an unit inverter. And for unit inverter it was R. Let us consider for unit inverter for this circuit it was R, this R. So this R should be equals to 3 R dash, right? Implies my R dash should be equals to R by 3, simply. This is what I have written here, R by 3. This is what I have written here, R by 3. Now how to achieve this, how to achieve a resistance of R by 3? If I have to reduce the resistance, that is I have to increase the current. To reduce the resistance, what I need to do? I need to increase the current. And what was the expression of current? It was mu Cox W by L into VGS minus VT into VDS minus VDS square by 2, right? Now mu Cox is fixed for a particular technology, I cannot change it. Okay, VGS VDS are the like what it is the variables which we will be changing. L is fixed for a given, L is generally taken as the minimum value. So what is the only thing that can increase my IDS or reduce my R? It is this W. That's why what we do, we increase the value of this W. Okay, as you can see, IDS by say VDS. Okay, let me take the equation in saturation condition. VGS minus VT, not VT, lambda VDS. Sorry, let me take normal condition only. VGS minus VT minus VDS by 2. Okay, so IDS by VDS is 1 by R, or implies VDS by IDS, which is equals to R is what? You will see VDS by IDS would be some constant divided by W. The W will come below, so it would be something divided by W. So resistance is inversely proportional to W. So if I increase W, if I make W twice, the resistance would become half, correct? So if I want to make a resistor as 1/3 of initial, I need to take W as thrice of the initial condition. That's why here W of 3 has been taken. And this is how we size a given circuit while ensuring minimum delay or the delay of a unit inverter. Now regarding these PMOS stacks, as these resistances are in parallel configuration, not in series configuration, so it is not going to increase my resistance. If all the 3 transistors are on, it would only reduce the resistance. And in the worst case possible, what will be the worst case? The worst case will be this transistor is off, this transistor is off, and only this transistor is working. Okay, best case would be R, that is all the 3 transistors are on. So R. So my net R would be something as 2R by 3. This would be net R. This is the best case. This all these 3 transistors are on. Okay, all these transistors are on. But in the worst case, what it will be? Worst case would be, so what happened? Fine. Worst case would be only one of these transistors will be on and the other 2 transistors would be off. In this case, my net resistance would be R, not 2R by 3. If it was 2r/3, it would be my contamination delay, the best case. And if it is r, it would be my worst case or propagation delay. Okay, so in this propagation delay, the worst it can be is r, that is the resistor, that is the resistance of my unit inverter. So I don't need to change anything in the previous design, in the previous value of w. So here, as it was 2, I will be taking the new w also as 2. Okay, understood? So it is saying same thing, that yes, anything. With, yes, for NMOS, for NMOS, this one, for this one. See, see. Uh, see, here an inverter is present, unit inverter is present. Okay, and unit inverter is present. Agree with me? Okay, so basically what we do, uh, the least is, say the least, the length, the minimum possible length is L, and the minimum possible W is W. Let me take it as this one. Okay, so it would be W by L, it would be W by L, and this would be 2W by L. Because why twice? Because mobility of PMOS is half. So in order to ensure rise time and fall time to be equal, I need equal amount of current. So equal amount of delay, I need to increase the current. So I take the W to be twice. Okay, correct? Now, in case of designing, what we do, instead of writing W by L, W by L, W by L every time, to make it simple, we just take this W by L ratio as 1. We write it as 1 and we write this as 2. Correct? So when it is mentioned, then it is 1, it is already been taken that the W value is the minimum possible W and the L value is minimum possible value L. When we will be writing here, instead of 1, if I write 2, this means my minimum possible length L is still present, only instead of 1W I am taking 2W. Okay, so for simplicity, we always write, instead of writing this 1WL and 2WL, I will be writing 1 and 2. Understood? Okay, fine. So here same thing is saying that for a rising output, the resistance of an individual PMOS must be R by 3. And we have seen for PMOS, I don't need to change the W. So I don't need to change the R. So initial R was fine. Initial R was R only, right? So I don't need an R of R by 3 in order to ensure an equal amount of fall time and rise time. Okay, fall time and rise time. So it's false. That's why it's false. Is it clear? Okay. And given that for a falling output, the resistance of an individual NMOS must be R by 3. Now we have seen for falling output and for equal rise time and fall time, what we need? We need the resistance to be, net resistance to be R. That is, we need the individual component resistance to be R by 3. That's why we need W of 3 or resistance of R by 3. So this is what that's why it's true. Understood? Okay, fine. Okay, fine. Okay. Let me move forward then. The next question, question number 6. Okay, question number 6 is what? Using the Elmore delay model, what is the T propagation delay rise for a 3-input NAND gate given the circuit below? See, here W is taken as 2 and W of NMOS is taken as 3. Why? The same reason I mentioned here. This one. That's why I need to ensure a resistance of R. So thrice W has been taken as 3 and 3. And as PMOS already the worst case would be R only. So we have kept it undisturbed as 2 only, the W value. Okay. And it is given the input 1 is 0 and input 2 and input 3 are 1. Now what does this mean? This means these capacitances are already discharged. These capacitances are already discharged, like I was talking in this case, if you remember. Okay, that these capacitances, whatever charge was stored, has already been discharged to ground here. Okay. Okay, so now what I need to find, I need to find using the Elmore delay model, what is TPDR. It's simple. T propagation delay rise would be equals to, so what are the capacitances involved here? uh, the input, it will, sorry, so each input will see how much capacitance. Say this two are shorted, right? So this will see a capacitance of how much? 2C plus 3C, that is 5C, correct? And output will see a capacitance of how much? 2C plus 2C plus 2C plus 3C. So 6C plus 3C is 9C, correct? And as these are already discharged, I don't need to consider them. So the model, I think it has been asked for rise. Okay, fine. And as it is 0, this one would be on and this two would be off, as these are 1. Okay, just only one PMOS is working. So it would be R PMOS 9C. Okay, and there are other capacitances present there, but they have already been discharged, so I don't need to worry about them. And moreover, this one is also off, these two are on, so no need to worry about them. So my simple, what would be my propagation delay? It would be R PMOS into 9C. Then R PMOS is R, so R into 9C, so 9RC. Simple, 9RC, nothing, it's very simple. Now you might ask why I'm not using this ln2 log2 value 0.693, because I am taking the input as, if I take an ideal input, I'll be writing as ln2rc, and if it is an non-ideal input like this with finite rise time and fall time, then I'll be taking simple simple RC. It would be much more appropriate, much more accurate, not appropriate, much more accurate. Okay, any confusion? Sure. Like if they don't give you the width of any, like of a given architecture, you were saying, see, when we design a circuit in digital, not memory and all, just simple digital, what do? We try to ensure that this rise time, T rise is equals to T fall, and it is equals to that of an unit inverter. Okay, so for unit inverter, so that's why the value of R that will be required, so you can design any circuit now. Okay, give me an arbitrary circuit. Say I am designing an n input NAND gate. Okay, an n input NAND gate. I have the PMOS stack, and I have n NAND gates in series with each other. My drawing is really bad, my handwriting is really bad, pardon me for that, but I hope you will understand the concepts and you will not require a good handwriting to understand it. By just listening to me, you will understand it. Okay, so basically now there are n such transistors. Okay, now what I need to do, I need to ensure a resistance of R. Okay, and if it was simple, if L was W was taken to be minimum, what would be my new resistance? R plus R n times, so it will be NR. But I need the resistance to be minimum, so what to do? I need each resistance to be R by N. So if I need the resistance to be R by N, how much I need, how much should I scale the W? N times. So my W would become, instead of 1, it would now become, instead of 1, it would now become W, N. W should be equals to N. Instead of 1, I have to take the N to be W to be N. So all this should be N. And as PMOS is involved and they are all in parallel, same logic, it would still be 2. Now you have designed a n input NAND gate. So you can design any circuit. Okay, if you know the basics, and if you know inverter and the basics, then you can design any circuit. Okay, so that's the idea behind it. I hope it's clear to you. Okay, most sure. Equals to R. Okay, now let's move to the next question. What is the T propagation delay fall for a 3 NAND gate driving H identical NAND gates? Okay, fine. Let me wrap it. Okay. So question is 3 input NAND gate. Let me draw a 3 input NAND gate. Fine. This is my output. These three are my input. Okay, this is VDD and this is ground. So, and what it is saying, driving H identical NAND gates. Okay, let me just let me not draw it again and again. Let me just draw an 3 input NAND gate here. Basically, this gate is identical to this gate. Okay, okay, this is output 1, output 2, output 3. Okay, so they have asked us to find the propagation delay falling. So if falling has been asked, I don't need to consider this pull up network. I only need to consider this pull down network. Okay, now what are the capacitances that are involved? Let me draw them. So here I'll be getting a capacitance of 3C. Let me first do the sizing. So it should be 3 3 3. Okay, so the capacitances would be here, it would be here, it would be 3C due to this one. Here it would be 3C due to this one, and here it would be again 3C due to this one. And due to this three PMOSes, I'll get a capacitance of 2C plus 2C plus 2C, that is 6C. 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 And what would be the capacitance at the input nodes? See, like this one, these two would be connected. Let me call it A, or input 1. This one and this one would be connected. I'll be calling them B. And this one and this one would be connected. Let me call it C. Okay. So what is the input capacitance it is looking at? The input capacitance is 2C plus 3C. So this capacitance would be equals to 5C. Correct? That is, this capacitance, because these two are identical gates, right? This and these are identical gates. So this capacitance would be equals to 5C. Okay. Okay. So now for the falling edge, let me consider the pull down network separately. So what would be my pull down network? It would be simply okay, this is my output. What would be the resistances? There are 3 NMOSes. What would be each resistance? As W equal to 3, each resistance would be R by 3. Be careful while doing this. Okay, and the capacitance would be 3C, 3C, and how much? 3C due to this one, and this 6C due to this PMOS, so total 9C. I am not considering this 5C one. I am not considering it right now. I will be considering it later on, because there are how many? There are H identical such gates, right? There are H identical such gates. So I will be considering this later on, this 5C. So if I do the Elmore delay model, what would be my Elmore delay resistance? So Elmore delay resistance would be T propagation delay falling would be equals to, simple. First I will be considering this case, it would be R by 3 into 3C. Then I will be considering this path, so it would be R by 3 plus R by 3, 2R by 3 into 3C. Then I will be considering this path, so it would be R by 3 plus R by 3 plus R by 3 into 3C. Manik, can you kindly mute yourself? Noise is coming. Okay, that's fine, no need to be sorry. See, so it would be basically 3 and 3, so it would be RC plus 2RC plus how much? 3, how much it would be? R into 3C, 3RC. Oh, no, here the capacitance is how much? Here it is 9C, right? So it would be 9C, so it would be 3 so it would be how much? R by, so 3 into R by 3, so 3 R into 9C, so 9RC. So RC plus 2RC plus 9RC, 12RC. Okay, fine. Now due to this H such second stage NAND gates, what would be the propagation delay for them? Sorry, so sorry, so the propagation delay for such circuits, there are H such circuits, right? And each circuit is providing an capacitance of, load capacitance of 5C. So for H parallel combination such NAND gates, my net capacitance would be 5C into H, correct? So and the resistance that it is seeing is still this one, still this path is the resistive path, that is R. So it would become, the circuit would become something like this. It would still be R, and this would be 5C into H. So its delay would become 5CH into R, it is 5RCH, correct? So my net propagation delay would become, T propagation delay falling would become this one plus this one, 12RC plus 5RCH, correct? RC plus 5RCH. Where is the option? This one, 12RC plus 5RCH. Clear? I hope it's clear. Okay, now we could have found it out for this we have found it for the falling edge, we could have found it for the rising edge also. It would have been similar, because 5 RCH term would have been common, and instead of this this Elmore delay model, we would have considered simply this one, this 2C plus C, so it would have become 3RC plus sorry, not 3C, 9C would also come. See, let me also do it for the propagation one also. For the propagation one, it would have come, sorry, the rising one, it would have come something like this. This is output, this is VDD, this is R, this is R. Okay, So it would have come, if you solve it, it is r by 3, it is 9c, it is 3c. If you solve it, you will get something as how much you will get, 9rc plus 3rc, something as maybe 12rc you will be getting. Okay, for this one, the rising one, they have not asked you the rising one, but this is the, with same similar approach you can do it for the rising propagation delay as well. Okay, okay, let me move to the next question. What is the normalized linear delay for a 2-input NOR gate, considering h is the electrical effort? Okay, so h is the electrical effort. 11. Need more space. So fine. Okay. It has been asked 2-input NOR gate. Let me draw the 2-input NOR gate first. This is output. So these are my inputs. So let me consider these two are connected. Okay. So what would be the sizes? Initially PMOS was 2, but as now I am using a stack of 2 PMOSes in the pull-up network, so I need the resistance to be same. So I should make the W of PMOSes double the initial value, and initial value was 2, so now it would become 4. Okay, and NMOSes, as they are parallelly connected, I don't need to change its values, because worst case would be R. So I will be keeping the W of NMOSes as same as the unity inverter case. So it would be 1, it would be 1. Okay, so what will be the capacitances? The input capacitance would be 4C plus 1C, 5C. And in the output, how much capacitance has been connected? It is 1C plus 1C plus 4C, so it is 6C. 1C plus 1C plus 4C, so it is 6C. 6C of capacitance. Okay, now we know what is the value of this normalized delay. It is propagation delay plus electrical effort plus logical effort into electrical effort divided by the delay of an unit inverter, which is 3RC, right? So D would be equals to propagation delay. First of all, what will be my propagation delay in this case? Let us find it out. So propagation delay is 6C, that is the capacitance, into R. How much is R? R is R, that is my initial resistance, because I am designing it in such a way that my R doesn't change. That is, my rise time and fall time doesn't change. Okay, so 6C, R is my propagation delay. What is my electrical effort? It has been given electrical effort is H. It is H. And what is my logical effort? What is logical effort of a NOR gate? We have to find it out. What is logical effort's definition? It is the ratio of basically logical effort. What does logical effort tell you? Logical effort tells you that your inverter is doing how much more work compared to a unit inverter to do the same amount of charging or discharging, that is to do the same amount of work. So how much more work has been done by this by your circuit compared to a unit inverter to charge the capacitance to the same voltage. This is what the logical effort is giving you, the information it is giving you. Okay, so what it would be? It would be how much input capacitance you are getting? You are getting 1C plus 4C, 5C into R. Okay, by 3RC. 3RC is the delay of a unit inverter. So you will be getting 6RC by 3RC, that is 2, and RC will cancel. It would be 5 by 3 into H. So this is my normalized parasitic delay. This is my normalized, this is my electrical effort, and this is logical effort, and this is my electrical effort. So 3RC is the delay of an inverter, unit inverter delay, and it is the delay of your circuit, this one. So the ratio of these two is giving you how much more work your circuit is doing to charge the capacitance to the same value. Basically what we are doing, as circuit the capacitance is increasing, we are increasing the current also. That is, we are driving more current. More current means more amount of energy, right? I square R. Okay, so that is, our circuit is doing almost 5 by 3 times more work than a unit inverter to charge the output to the same voltage level. Okay, I hope it's clear. So the answer will be 2 plus 5 by 3 H. 2 plus 5 by 3 H, this one. Okay, any confusion? Okay, if there are no confusions, I can move forward then. Okay, question number 9. Select the true statements. Fine. So here they are giving us the definitions of parasitic delay and logical effort, and asking us which definition is correct. Okay, so first one is normalized parasitic delay is defined as the ratio of capacitance of the inverter to the capacitance at the output node. So this is the normalized capacitance delay, P. Okay, so what is P? P is basically, it is the ratio of the output capacitance that we are getting, the capacitance that we are getting at the output node by the capacitance of a unit inverter. Okay, the capacitance, or the yes, of the unit inverter 3C. Okay, as R is same, we can cancel this R. This R is same in both the cases, so we can omit them. So it is basically the definition, ratio of output capacitance by capacitance of a unit inverter. So as it is, the first condition is given as capacitance of the inverter to the output node, the reverse is given, it is false. Correct? So first statement is wrong, it is the other way around. Second statement is normalized logical effort is defined as, this one, G, is defined as the ratio of input capacitance of a given gate to that of an inverter capable of delivering the same amount of output current. Very important line, this line is same amount of output current. So the statement says that it is the capacitance of a given gate by capacitance of an inverter capable of driving the same amount of output current. It is not saying an unit inverter, it is saying that of an inverter which is capable of delivering the same amount of output current. Very important line. Same amount of output current means, let me tell you what does this line, this part means. See, I can design a NAND gate like this. This is my PMOS stack and this is my NMOS stack. Correct? This would be by values. Sorry, this would be the values. Two input NAND gate. Now to find the logical effort, I'll be taking the capacitance of this one and divide it by the capacitance of an unit inverter. Okay, but now what if I scale this one to a value of 2n? I want the delay to be much less, so I want much more amount of current, so I have scaled it to a value of 2n instead of n. So in the upper, an extra n term will be added. So will my logical effort going to increase? No, it will not going to increase. Why? Because the definition is such, the output current should be similar to that of an inverter. Then instead of considering this inverter, which initially we are considering 1 and 2, we'll be considering a new inverter which is able to deliver the same amount of current. That is, we have to scale the unit inverter also to the value of n. Okay, so here also an n will come, they will cancel it out, and my g would remain same. So g value doesn't change if I have an architecture and a design and I'm simply scaling all the values, like I'm scaling all the w's, my net logical effort will not change. And this can be also thought of as, but also understood by, with scaling my resistance is decreasing but my capacitance is increasing, right? Resistance is decreasing by, say, I'm by factor n, I'm scaling it by n, so my resistance is decreasing by factor n, but at the same time my capacitance is increasing by a factor n. So this, so net RC would be R by n into Cn, so n would cancel out, net delay would be same, net logical effort would be same, net amount of work this circuit would be doing more than the unit, the inverter would be same. Okay, that is, it is the point. So this line delivering the same output current means this thing that I just talked now. Okay, and so the definition that they have given, capacitance of a given gate by capacitance of inverter delivering the same current, is correct, so it would be true. Okay, and the third statement is, normalized parasitic delay is defined as the ratio of capacitance of the output node to the capacitance of the inverter capable of delivering the same amount of output current. So it is matching the definition of parasitic delay, so it is true. Fourth statement is, normalized logical effort is defined as the ratio of capacitance of an inverter capable of delivering the same output current to that of an input capacitance of the gate. So now the definition given is reverse of G. So it is not G, it is equals to G inverse, logical effort inverse. So it's wrong. The definition given here is wrong. It's inverse of this one, what has been stated here. So it's false. So my correct sequence will be false, true, true, false. False, true, true, false. This one. Any doubt? Actually, I am giving you a lot of information. Something you might not be requiring it right now in solving this question, but I feel that these things are required in order to understand this subject. That's why I am telling you. Okay, that's why I am emphasizing these points, the small points, but they are very important in understanding the concepts. Okay, if any confusion is there, we can look into it. Yes, Netra. So for an 3 input NMOS NAND gate, it would be 3n. For a 2 input NAND gate, it should be 2n. For an n input NAND gate, it should be nn. Okay, or for a p input NAND gate, it should be pn. Understood? Because 3 is not fixed here. Okay, 3 is coming from where? It is coming from, we want the same resistor. Like I think I explained that. From here I explained it. Remember, in this position, if there are n such gates available, then my transistor sizing should be n. If there are 2 gates available, if there is only 1 gate available, that means it is an inverter, right? So n should be 1. If there are 2 gates, 2 NMOS present, so it should be 2n. So it should be 2. If there are 3 present, it should be 3. If there are n such transistors present in the PMOS NMOS stack, it should be n. As simple as that. Okay, is it clear, Netra? Okay, fine. Okay, then let us move to the last question of the day. The question is, the TPDF propagation delay fall of an input NAND gate as per the Elmore delay model, is. Now let's look into it. It will take some small amount of time, and if you can do this circuit by yourself, you can do any circuit, all the circuits that I have discussed till now. Okay, so let me draw an n input NAND gate for you, and NAND gate with n inputs, n input NAND gate. Let me draw it here. Let's make this question a little more interactive. You will be saying what will be the values that I will be writing here. I have told it many times in today's class, so you should be able to help me in designing it. Okay, so there are n PMOSes and n NMOSes present here. Okay, this is my output node. Okay, now tell me, what would be the value of this PMOS? What W's? What would be its strength? What would the W's be? Anyone? Yes, it would be 2. Correct. And for the NMOSes, these things, what it should be? W should be how much? Yes, exactly, N. Okay, so what are the capacitances? So what will be the capacitance here? Let us look into this easy one first. As these are connected, what will be the capacitance here? This capacitance, how much it would be? NC from this one and 2C from this one. So what will be the capacitance here? Yes, N plus 2C. N plus 2C. Okay, and what will be the capacitances here? What will be the capacitance here? Or this capacitance here? How much it should be? It's NC, correct? Because the transistor sizes are N. Okay, so it should be NC. Now what would be this final output capacitance here? Anyone? From this one it will come NC, and how much would be the contribution from this N PMOSes? NC plus what? Yes, as there are n number of PMOSes with 2C capacitances in parallel, so it should be 2 n of 2C, that is 2NC. So net would be 3NC, correct? Should be 3NC. Okay, fine. Now let's move forward. Okay, now let me it has been asked to find the falling, so I'll be considering the NMOS stack now. Let me draw the Elmore Delay circuit, the RC circuit for the NMOS stack. Okay, this is my output node. So what will be the resistance here? What would be the resistance here? This resistance will be how much? As it has been R by, yes, R by N. So all the resistances would be R by N. R by N. And the capacitances would be 3C. Sorry, NC, as it has been scaled by N, factor N. 3C, 3C. And what would be the capacitance here? As you have the capacitance here would be NC plus 2NC, that is 3NC, correct? Now let's find the propagation delay, fall or rise, fall I think, right? Fall, using the Elmore Delay model. Simple. First this one is discharging how much? NC into R by N, first one. Second, this one is discharging. Okay. Okay. So first, now this one is discharging, right? This one is discharging now. This one is discharging. So how much it would be? R by n plus R by n into NC. Correct? Third one would be R by n plus R by n plus R by n 3 times into NC. This one would be how much? Until how much? Until this one. Until this one. So it should be plus dot 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 plus how much? It would be n minus 1 R by n into NC. Now why n minus 1 I have considered at not n? Because the final n is connected with 3nc, not 3c. Sorry, no, what I am writing 3c, not nc. The final one is not connected with nc, rather it is connected with 3nc. Okay, so plus, that's why I have written n minus 1 plus R by n into 3nc. This final term, this 3nc, R by n into 3nc. This one. Okay, so now what it would be? N cancel. It would be R. It would be RC plus 2RC plus dot 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 plus n minus 1 RC plus 3RC, right? Now what is this? This is what? This is sum of an AP, arithmetic progression. From school days you are studying it. What will be the formula? Sum of an AP? Anyone? It is n by 2 a plus an, or n by 2 2a plus n minus 1 into d. So this is sum of an AP, right? Therefore this should be equals to how much? N by 2. N is how much here? N minus 1. So it would be n minus 1 by 2. A is RC, so 2a twice RC plus n minus 1. N minus 1 is capital N minus 1 minus 1 into d is again RC plus this term, this is 3RC. Solve it. How much it is? N minus 1 by 2. It is so it is not small, it is capital N. It is n by 2, right? So n minus 1 by 2. 2RC minus 2RC, it will cancel, so it will become 2RC plus nRC minus 2RC plus 3RC. So 2RC cancel, so n minus 1 by 2 into nRC plus 3RC. Okay, take RC as common, you will get n square minus n plus, as if I take this fraction, it will become 3RC will become 6. It will become something like this. So what are the possible answers given in which form? 5RC, okay, by 2 n square minus, have I done any mistake? nRC, what was the answer I was getting initially? I think I have done a mistake here. Just give me a minute. N minus 1 by 2, 2RC plus n minus 2RC plus 3 nRC. Here n will come. Okay. Will it come? No, it will not. Yes, it will come. Okay, so it will become 3RCN 6RCN plus 6n, so it will become RC by 2 n square plus 5n. Okay, answer is RC by 2 n square plus 5n. This one, first one is the correct answer. Any confusion? Anyone? Yes. Like okay, fall time has been given. You want me to explain the rise time also, right? I just hope that rise time is not the question that sir has asked for this time's assignment. Okay, then let me explain this one also. See, for rise time it will be much simpler. Why? Because R would be R only. Okay, let me draw it here only, different color. This would be R. Okay, capacitance would be how much? 3nc. Okay, and this terms will have no effect. This terms will have no effect because it is in the falling one. So simple. And will the NC's effect? Let me check. Okay, in the linear delay model, this NC's will have no effect, right? But in the Elmore delay model, you have to consider this also. Only one will be on. So at a time, in the worst case, what happens? Only one transistor is off, others are on, others are off. So simply only one NMOS will be on, other NMOSes will be off. So it would become R by N, and here the capacitor will become NC. Okay, now solve this one, you will get the answer. Very easy. I hope you can solve this. This is the output. What it would be? It would be R into 3NC plus R by N plus R into NC, something like this you will get. It should be equals to 3RNC plus R plus Rn, N square C, R plus Rn, R plus Rn, something like this, R plus Rn, something like this you will get. Okay, and then cancel. Sorry. N square C. I hope you can solve this by yourself also. 3RNC plus how much it would be? N cancel. So R plus Rn into C. Something like this. Of this order it will come. Okay. You can do it. You can do it and check it yourself. Okay. Any more questions regarding anything? Okay, I wanted to talk one more thing. Like, see here all the time sir is talking about this fan out 4, h equals to 4. You will see that, well, in this course this number 4 is going to come again and again. Okay, so what is so special about this number 4? What is so special about this number 4? 4, fan out of 4, and where everywhere you are seeing that h equals to 4, sir is taking y. What is so special about this number 4? Basically what happens, see, I have designed a complex circuit. Okay, my input is this, my output is this, and there is some complex circuit inside this one, inside this black box. Now what happens, I can keep on increasing the W's in the transistor stack. Okay, and I can increase W in this one, in this one, in this one, or in the black box, and this would result in lower value of, say, I've increased it by factor n. or a factor k. So my rate R would reduce by factor k, my capacitance would increase by factor k. So my net propagation delay will not be sorry, net parasitic delay will not be affected, but my G is going to G and H are going to change the load capacitance terms. So how much work is needed to be done for getting the optimum delay, that is the least amount of delay? If you solve it using this I equal to c dvdt, and if you do this calculation, you will find that we generally get, if you find the derivative of the energy derivative of it, and you will find the least amount of delay, you will find that we get the least delay when all the stages present in a circuit are doing equal amount of work. Okay, when all the stages are doing equal amount of work, on that time the delay that we encounter is the least. Now to, for say I've been given a circuit, there are some x number of terms which are not, which are designed which I want to further improve the delay. What I do, I insert a chain of buffers between them. Okay, so that the net scaling is in such a manner that all the part does equal amount of work and I get the net delay as minimum. Okay, so now how many elements, how many inverters, or how many elements should be there inside this one? If you solve that equation, if you find the derivative that will give you the least delay, you will get the resulting number as 3.59, which is almost equals to 4. Okay, as I cannot use 3 number of 3.5 in fraction number of elements, I am using 4. So if in a circuit, if you have to if you are given a number of circuits and if you want to further reduce the delay, optimize the delay, what we do, we add an buffer chain or inverter chain of in a factor of 4. That is, we will either be inserting 4 inverters, or will be inserting 8 inverters, or 12 inverters, or 16 inverters, in such a way. When we will be solving this that equation, that minimum delay problem, and if you find the derivative and if you find the solution, on that time we are getting this result. From here this number 4 is coming. That's why this number 4 is a magical number in VLSI system design, or in VLSI circuit designs. Okay, that's why you'll be getting this number 4 again and again. That is why we are considering this 1 out of 4 and all the things, all the number, why we are always playing with this number 4. Okay, I wanted to just inform you. I am not giving you the mathematics of it. I can give you, it will take some time, but for your understanding only, just keep in mind that's why we are using this number 4. Okay, any question regarding today's class? This part is extra, just for your information I have given you this one. No need, just keep in mind. Any question regarding today's class? Yes, Netra. Analysis of CMOS inverter. Okay, tell me. Okay. Okay. Like this you are talking, you are saying. Okay, fine, then. Okay. Okay, see, it is like, first of all, do you know about body effect? I think I mentioned in one of the classes a little bit. See what happens, this body terminal, generally if we apply some voltage here, the VT of my transistor shifts, my VT of the transistor changes. Okay, so in order to remove this body effect, this body is generally connected with the ground, and here this body is generally connected with VDD, so that my VBS is 0, because this Vt term, if you see the expression of Vt, there is an proportionality with VVS, not directly proportional, under root under something or exponential something, I don't remember exactly, I think root under something. To remove this VBS dependency, we short this body and source. As this is drain and this is body and this is source, we short this body and source. That's why we are considering the capacitance here is between body and ground, and here between body and VDD. Okay, now one thing, the capacitance that you are talking about, that why the effective capacitance has been taken, the net capacitance has been taken like with ground only, I think this is your question, right? Okay, so basically these are not physical significance, you cannot find much, uh, like this is by VDD and ground, here we are referring to some reference voltages. Okay, so while doing the analysis you can, and I think this capacitance will this capacitance, I have not seen such that lecture that you are talking about, but I think this capacitance, uh, see, what is my aim? My aim is to charge this capacitance or discharge this capacitance, right? So here, while discharging, this capacitance should come into picture and it would be discharged to ground, and this capacitor will come to picture and this will be charged to VDD. Okay, so basically I can take these capacitances out and I can clump them together, and I can either say that both the say if it is C, if it is, and this is C, I can see there is a net capacitance to C, which is getting charged to VDD or discharged to ground. I can say both. Okay, I can simply clumping them together for mathematical ease, nothing else. Okay, and I have not seen that lecture, but how much, as per my understanding, these two capacitances would not come together and there would be no need to clump them. I don't know in which part of the lecture sir is told, but basically because this is always comes in the discharging path and this comes in the charging path, so generally you don't need to consider them much, you don't need to consider them together. Okay, but maybe in some place sir is told that where he has done the analysis while taking both them connected to a virtual ground or something like that for ease of mathematical analysis, this can be this might have happened, but I don't know exactly what he has done. Okay, with 3 lectures. Okay, I might have I'm not seeing all the lectures actually, so I don't know. I think, see, in contamination delay he was talking about an inverter or a NAND gate or something like that. Inverter, okay. Generally it's easy to understand the contamination delay in terms of NAND gates and all, like I told you that you have to discharge these parts also, where it is gone, like I told you that we have to discharge these parts also. If we consider, then it will be if they are already considered discharge, it is considered as contamination delay, else it is considered as propagation delay. But using inverter, it might be thought of that we also need to discharge these body capacitances. As I mentioned, there are 5 kind of capacitances, and we only consider this drain and source capacitances. Here the source capacitance is connected with ground, so no need to discharge it. Here it is already connected to VDD, so no need to discharge it. But these body capacitances, in some cases, like if it is an FDSY structure, then you need to charge or discharge it, and in some cases this might affect your circuit also. So I think on that time he was trying to introduce you to this concept. He has talked about this, that these capacitances, body capacitances, can be clumped together, and as while one is charging, the other is discharging, we can clump them together and for mathematical ease. I think something might of that sort might have happened. Okay, it was for a NOR gate. See, in NAND gate, the contamination delay basically means the smallest delay, the best case delay or the smallest delay, and the propagation delay means the worst case delay or the highest amount of delay that your circuit can encounter. Okay, now in inverter, uh, the source capacitances would not come into picture. Okay, as I already mentioned, they're already connected to the rail to rail swing, VDD and ground. They're already connected to VDD and ground. So this should not come into picture. The only capacitances left are your body capacitances. That's why Sir has, I think Sir has introduced you to with this term. He has clumped them together. Okay. Uh, yes, Nazma. Okay. 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 That is obvious, right? Because uh, here, when we are calculating the net capacitance of of a given circuit, there are multiple capacitances come into picture. Okay, let me show you. Not only this, there will be much more, many more terms. Okay. Yes. Yes, please. Okay. Okay. Just give me 2 minutes. Let me talk about this. Then I'll be going on contamination delay. Okay. Okay. See, when you're designing a circuit, what is capacitance? Capacitance we are trying to find between my final VDD and ground. I want to find the net. I want to find the capacitance. Okay, so basically this is a black box with many R's and many C's. I want to find the net. I want to find the resistances and capacitances. Okay, so there are five capacitive terms due to these things that I already mentioned. There are other capacitances like interconnects, because simple metals are not used generally. You use some different metals of titanium, nickel and all. They introduce interconnect capacitances. And there are ICs are made in multiple levels. Okay, as you go up, the resistance reduces because we are using more amount of metals. There is something called back end of the line, that is after metallization, before metallization, what kind of interconnects can be used. Many things, many capacitances come. There are something called as fringing capacitances between metal to metal, like gate and drain. So there are some fringing capacitances present. Okay, so for ease of analysis, like I mentioned, we can clump all the capacitances together, that my net capacitance between my VDD, my rail to rail, VDD and ground is this much. And as they are all connected in, almost all of them are connected in parallel combination, I can simply take them together and take the net capacitances, the CS, the sum of them. Okay, Nitra, is it is my argument seems sufficiently do my argument seems to have sufficient amount of strength to make you believe in it? Okay, so basically you have to think analytically, that why this thing has been taken, why he is approximating them. Because in electrical circuits, these rail to rail swings are the one between which we were trying to do all the analysis. So it can be take like this circuit is connected to VDD. Okay, and it is connected to say VDD dash, two voltages. Now I can take this as VDD plus VDD dash, and I can take this as ground. Sorry, VDD minus VDD dash, and I can take this as ground. Right? It is simply about references that I am using. Okay, so that's why you can we can adjust the voltages because it is the difference in the rail to rail that we are considering, and not the absolute voltages as such. Okay, that's why we can clump multiple circuits together for ease of calculation at many places. Okay, I hope that will make you that will make it clear. Okay, and now yes, Nazma, what do you want to ask? You can go ahead. Contamination delay. Okay, what is the confusion? Okay, yes. Okay, in the, I think you have missed the first part of the class, because I have talked about it. But let me restate what I said. Okay, see, let me take an two input NAND gate, simple circuit, two input NAND gate. Okay, so uh, propagation delay is the maximum amount of delay that your circuit can encounter. Okay, maximum amount of delay means the worst case, the worst delay that my circuit can encounter. Okay, say for example here, if I take the Elmore delay model, it would be 2, it would be 2, it would be 2, it would be 2. Okay, so here it would come, 2c because of this one, and here it would come 2c plus 4c, that is 6c. You do this, this and this, it will come 6c. Correct? Now propagation delay will consider that this 6c, this 2c, all are needed to be discharged. While changing the output from VDD to ground, I need to discharge this 6c also, this 2c also through this path. This is my propagation delay. Okay, that is my initially my output was, say it is t equals to 0. Initially my output was low. At t equal to 0, it has become high. Both these outputs, this is A, this is A, this is B. Okay, now let us consider a situation where my B has been turned on much before A. That is, B has been on before A. So what will happen? The charge that was present in 2C has already been discharged before A has arrived. Okay, so now I need, when A arrives at t equals to 0, I only need to discharge the 6C, and as this 2C has already been discharged, right, I only need to discharge this 6C, and this 2C has already been discharged. So what will happen? The delay that will be required will be will be less than the worst case delay. Okay, and this is called the delay which will be the least, or the best case delay, or the least absolute, where in absolute values it will be the least delay, also called the best case delay or contamination delay. Best case delay is called as contamination delay. Okay, that is, my intermediate nodes has already been discharged. For NAND gate and for NOR gate, it has already been charged. For NAND gate, the intermediate nodes have already been discharged before my critical input is coming. Okay, so I will consider only one capacitance as other capacitance has already been discharged, so I will get delay much less than it. So it is called as contamination delay or best case delay. Is it clear, Nazma? Okay, okay, fine, good. Anyone else? Anything? Yes. Okay. Okay. Sure, I'll try. Okay, noise. Okay. 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 You have to give me all the conditions. I cannot, like, I was unable to capture all the conditions. VDD was given as 1 volt then, and what was the next condition? Noise signal is okay. So noise signal is less than this, so my noise margin should be more than 0.5 volt. Then yes, so okay, static current is 0, fine. See what they are saying that if it is your 0, if it is your VDD, okay, generally what we do, VDD by 2, if anything above it we are considering as logic 1, anything below it is considering as logic how much, logic 0. But here it is saying that up to the noise signal is such that it can take all these values. Okay, and all these values it can take. Okay, that is, it can take up to something which is just less than 0.5. And so we have to, what we have to do, we have to design the circuit in such a way that my noise margin is not 0.5. So we have to design the circuit in such a way that our circuit, the output of the voltage is in such a way that it is very much close to VDD and ground, so that even if a noise of 0.5 arrives, it doesn't cross this VDD by 2 value. Okay, is it clear, Nazma? And anything else like regarding this question, anything that I'm missing, any point? Oh, high skew, low skew. See, in the previous lecture, if you go and see my videos in the YouTube, you will see that when we move the when an inverter, like when I introduce skewness to an inverter, one of the noise margin increases, the another decreases, right? Okay, then noise signal is less than 0.5 volt. Okay, so how much I'm understanding, the noise signal is not affecting both the signals, it is only affecting this one. I think the ground signal it is only affecting. Okay, so I need a larger noise margin low, and I can afford a small noise margin high, something like this. So you have to design the skewness in such a way that your noise margin high reduces and noise margin low increases. Simple question. Like the framing of the question is beautiful. He has framed the question very beautifully so that you think what is happening. But basically the mathematics is what I have described. I discussed in the previous class. The mathematics remains same. Only the formulation has been changed. Okay, I hope you'll be able to do it. There's nothing like many much fancy and nothing is there. It will be simple only. I forgot. I have to check it. Okay, you just go and see my last lecture. Sure, sure, sure. You will get it there. Okay, most welcome. Anything else? Anyone? Okay, if Uttara, Netra, Nazma, anything, you can ask me. Okay, okay, yes, Nazma. Okay, sure. Okay, 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 okay. Just let me draw a transmission kit for you. Okay, so there is an PMOS, there is an NMOS. Okay, now tell me the input is something like this. Okay, fine. Then okay, fine. Rising step input. Then the NMOS. Okay. Yes, correct. Oh, like see, simple thing. Here, if you apply VDD, you are applying VDD at gate. Okay, so this is your VS, right? So, as this one is charging, your VS is increasing, right? VS is increasing. Okay, so Vs, like my VGS minus VT should be greater than 0. Correct? VG is VDD minus Vs minus VT should be greater than 0. So VDD minus VT should be greater than Vs. Sorry, is it right? VGS, Vs. Yes, so my Vs should not, my Vs cannot cross this VDD minus VT value. Simple thing, simple calculation. If you have any confusion, you can simply write a mail to sir that sir, simple logic is suggesting this. Why you have marked it, like given the marking scheme in such a way. Like if this is the statement that you are saying, then my Vs would be charged. Oh, okay. See. See, this would have been the condition for a pass transistor logic. Okay, if this was my circuit, it would have been charged up to VDD minus VTN, but it is a transmission gate, right? So transmission gate, even PMOS is working, and PMOS will charge it to VDD. I like I that it's a transmission gate. It came out of gone out of my mind. See, VDD will be able to charge it up to VDD minus VTN. Fine, but PMOS can charge it up to VDD. It is strong one. VDD, yes. Yes, up to 0 to VDD minus VTN, NMOS is on. After that, NMOS will go to cutoff. Yes, uh, PMOS will be in on condition. Yes. Oh, the third statement is saying that up to VTN, it would be that my NMOS would be on. This is the statement, right? Okay, then yes, it is. It can happen like in the first 2 weeks that I have discussed. I think I have discussed you two questions where the answer that has been provided by them was wrong. If you remember, if you recall it. See, it happens. It like the who are solving this. What happens generally in NPTEL lectures? There are two TS. Okay, one. Yes. Okay. So these are created in such a way that you get confused. Okay, and if your understanding is clear, if your concept is clear, you will not get confused. If okay, actually, see what happens. There are two like teaching assistants to a professor. Okay, one of them solves the assignment. Okay, he is under supervision of sir. He reports to sir. So there, like even when we are doing, we might do mistakes, right? Like human error is possible. And one, yes, yeah, I understood. See, yeah, that's why like okay. Okay, I understand your point, but telling it to me, I think I won't be able to help you. See, it's fine. Like, in which college you are at now? You are doing bachelor's, I think, right? See. No. Let me tell you something. When we are studying in our colleges, we are doing our MTech and PhD. The courses that we do, if the course is say the full total marks is around into the exam is happening in 40 marks, the average marks of the class generally doesn't cross 6 or 7, because they will be giving you so difficult question that it will what it will do, it will confuse you, but at the end of the day it will enhance your thinking ability. So the aim of this course is not to give someone some marks, some grades and all, because NPTEL, what we will do with the marks, with the knowledge, it will be useful to you, right? So they are trying to enhance your thinking capability, nothing else. And even I don't know sir, even I have never talked with sir, even I have not mailed him. He is from Triple IT Bangalore, I am from IIT Kanpur. Okay, so I have been award like I am a PMRF scholar, so I have to do 50 hours of teaching duty out of my college. It is the rule of government. Okay, that's why I have been assigned this. So if I was making the question, I would have definitely kept that in mind, so that it becomes more interactive and you guys enjoy doing it. And I think sir is also doing in such a way, but like human errors are possible, right? So some error might have happened. It is better you mail sir and contact him regarding this. He would be able to help you better. Okay, and don't get disheartened like what happens in 1 or 2 marks, nothing happens. And this certificate, it is not nothing like that the knowledge is important, right? If something, yes. Okay. Ari, you will pass it easily. Don't worry. Don't worry. So NPTEL courses can be taken as like your mandatory course for PhD. I don't know. Oh, nice. Which college? Like which college are you in? Okay. Okay, okay, nice, nice. I didn't know about this scheme. It's a nice scheme because the courses are really good in NPTEL, right? So the PG level courses. So yes, that's nice initiative. Okay, nice. Okay, you can simply mail it to sir regarding your problem. Okay, I like he'll be more than happy to help you. Even when you are doing our courses in IITs and all, this kind of thing happens because someone at the end of the day is solving it for you, right? This question they are professors are making, some students are solving, some of his student who has done this course previously. So human errors are possible at every stage, right? So we should also like accept this limitation of human beings, and we should take it constructively, and we can when if you ask sir, he will take it, I'm sure he will take it positively. Okay. Okay, best of luck. Okay, any more question, anyone? Okay, if there are no further questions, we can call it a day. So best of luck. uh, okay, then see you guys next week, next Friday. Thank you. Bye. Thank you.